Hi, in this lecture, I want to talk about modeling of control systems. Now, we have already looked at a closed loop control system as shown on the screen here. And we've said that one of our goals in this particular course is to be able to design controllers that can make sure that we get the output that we want. But to be able to design controllers, uh, uh, the kind of controllers that we want, what we want to do is if we are able to model this control system in some way using mathematical equations, we can do some analysis on them, and based on that analysis, we will be able to design these controllers. Okay, so that is where we are going, and that is the reason why we want to study about control system modeling. Now, if you want to convert a physical system into a mathematical model, uh, you know how to do that in certain cases, right? So, in the electrical case, for example, if you have an inductor, if you have a physical inductor, you know how to model it. Similarly, you know how to model a capacitor, write equations for the voltages and currents in the capacitor or in a resistor. And as it turns out, if you know this electrical equivalence, you are able to model systems in many different domains. So, so take a look at this. So there is a kind of an analogy between different physical systems. So, for example, in the electrical system, what you have is current, charge, voltage difference, and probably magnetic flux. And similar to these quantities, in mechanical systems, you have force, momentum, velocity difference, and in fluid systems, you have flow, volume, pressure difference. In thermal systems, you have heat flow, heat energy, and temperature difference. So, what I'm trying to say is that if you're able to kind of model one of these systems, then you should be able, with some instruction, to be able to model different kinds of systems. And this is very helpful because in control systems, not all control systems are fully electronic, right? So remember the boat steering example? So there was some electronics involved, but there was also a lot of physical things. And the reason why physical things start coming in, physical quantities start playing a role, is because most control systems are trying to control physical quantities. They're trying to control mechanical quantities or fluid flow rates, or temperatures, or things of that kind. So, based on this analogy, uh, let me just and let's just explore this analogy a little bit more. So, if you have an electrical inductance, you know the governing equation, and corresponding to the electrical inductance and the energy storage in an inductor, in other physical systems, you have like spring or a rotational spring or fluid inertia, and they mathematically behave very, very similar to how an inductor behaves in the electrical domain. Similarly, a capacitor is also similar to different kinds of quantities in the other domains, and so are the resistors. Now, with these analogies, you should be able to translate from one domain into the other. So, let's say you have to analyze a system in the fluid domain and you're just finding it very, very difficult. So you should be able to convert from that fluid domain into the electrical domain and analyze your system in that domain and be able to model that system in that sense, right? And even if you don't convert from one domain to another, still, I think the equations that I've just shown you, and I've kind of very deliberately just shown you very briefly, are able to convert these physical systems into mathematical models.